Dear students, let us continue our study in this paper of organic chemistry, and in this particular module we shall be studying about the addition reactions to the carbon-carbon multiple bonds, and we shall be paying emphasis to the electrophilic addition to alkenes. After studying this module, you shall be able to know about the various types of addition reactions of C-C multiple bonds. This is not a new topic to you, you have studied earlier also, but we will be going into variety of new reactions as well as some reactions that you have already studied. You shall also learn about how the electrophilic addition happens to alkenes, and you shall be made familiarized with the mechanistic pathways of the electrophilic additions. You shall acquire an understanding of the observed regio and stereochemistry of the addition product, and you shall be able to identify and know the synthetic importance of electrophilic addition reactions of alkenes. So dear students, let us begin with an overview to the addition reactions. An addition reaction is a reaction in which parts of a reactant are added to the two atoms that make up a double or a triple bond. For example, you are already aware with this very elementary addition reaction, that is addition of chlorine to ethene. As you can see in this equation, the two chlorine atoms are adding to these two carbon atoms. So, these two carbon atoms which hold this double bond are adding the parts of this addition or the adding reagent, which is chlorine, and correspondingly you are getting this. And notice that it is a reverse of an elimination reaction, because elimination reaction you will be removing atoms or groups and correspondingly making a double or a triple bond. So, here it is a reverse of elimination. Addition reactions can be grouped into four broad categories: electrophilic addition, nucleophilic addition, free radical addition, and concerted addition. Out of these, electrophilic and nucleophilic addition reactions, they involve ions, and that is why they are called as ionic addition reactions. On the other hand, the free radical additions and concerted addition reactions do not involve the formation of intermediate ions, and they are called as non-ionic addition reactions. Talking more in detail about these, electrophilic addition reactions involve the reaction of a positively charged species or positively polarized reagent, that is an electrophile, which is electron deficient, that takes place with a multiple bond, that is double or triple bond. The reaction leads to first the formation of a cationic intermediate, mostly the carbocation, to which the second electron rich part of the reagent attacks as a nucleophile, as you can see here. So, here you can see the alkene is first being attacked by X plus, which is the positive part is the electrophile, and you are getting a carbocation, and then this is followed by the remaining negative part of the reagent, that is Y minus here, and it is attacking on this carbocation, and ultimately you are getting X and Y part of the reagent adding to the double bond and leading to this addition product, and that is why it is electrophilic addition. In the nucleophilic addition, the electron rich reagents, which are nucleophiles, they attack the carbon-carbon multiple bond, and they result in first formation of a carbanion intermediate, which will be subsequently attacking or will get attached to the electron deficient part of the reagent. As you can see here, on this alkene, X minus is attacking first, which is a nucleophile, you get this carbanion, and then this is followed by attack with Y plus, which is the positive part, and you ultimately get the addition product. In free radical additions, addition of free radicals, which in turn are generated via light or free radical initiators, they take place to this carbon-carbon multiple bonds, and they will have chain initiation, propagation and termination steps like in any other free radical reaction that you are already aware with. So, you can see here the X2 is generating X dot, which is the free radical, and then the alkene is getting attacked with X dot, giving to this rise of this free radical intermediate, and then further it will be attacked with other free radicals in the initiation, propagation and termination steps. Coming to the concerted addition reactions. These are the reactions where the addition of reagents to multiple bonds, they occur in a concerted manner, that is in a single step without the formation of any ionic or radical intermediate. For example, the hydroboration of alkenes is a concerted process, as you can see here. This alkene, when it is attacked by BH3, the BH3 will be adding to this alkene simultaneously and gets attached at H and BH2 in the addition product. We will discuss more about this later. Now moving to the reactivity of carbon-carbon multiple bonds. Compounds which have unsaturated carbon-carbon bonds are more reactive than the corresponding alkanes and can undergo many type of reactions with various electrophilic or nucleophilic reagents or with free radicals. And of these, the electrophilic addition reactions constitute the most important aspect of their reactivity. The carbon-carbon bonds of a multiple bond are individually weaker than normal carbon-carbon single bonds. For example, to break a carbon-carbon bond will require 83 kilocalories of energy, while to break the additional double and triple bond, it would require 63 kilocalories and 54 kilocalories of energy respectively. Thus, addition reaction to carbon-carbon multiple bonds will fetch 20 to 30 kilocalories more energy than the corresponding cleavage of carbon-carbon single bond. This in turn can be attributed to the pi bonding, and pi bonding you are already familiar, is the sideways overlap of p orbitals, as you can see here, and this is present in the carbon-carbon multiple bonds, and these pi bonds are weaker than the sigma bonds. So, it is due to these pi bonds that there will be addition reaction which will be happening. So, the pi bonds break, sigma remain there, and in turn you will have the addition reaction. So, the pi bonding in unsaturated compounds also increases the electron density around the multiple bonds. So, in both double and triple bond you can see there will be electron density around that area, and this in turn makes them more prone towards the attack of various reagents, and especially the electrophilic reagents will be attracted because of this electron richness. Now, let us go into more details of electrophilic addition to alkenes, which is the focus in this module. The most common chemical transformation of a carbon-carbon double bond is the electrophilic addition reaction. Many reagents, organic as well as inorganic, they add up to the carbon-carbon double bond and provide various products of synthetic importance. Most of these additions are polar additions, that is, the reagent may have slightly positively charged part and a slightly negatively charged part, which are represented by delta plus and delta minus respectively. Due to the electronegativity difference, or the bond of the reagent may get polarized due to an added catalyst or solvent, etc. And this you can see here, that in this given reagent EY, E acquires delta plus and Y acquires delta minus. So, E will be then attracted as E plus, which gets attacked to the CC double bond, followed by the attack of Y minus, and there will be formation of this addition product. The initial attack of electrophile should occur perpendicular to the plane of the double bond and near the midpoint of the carbon-carbon bond. However, these polar additions can actually follow different mechanistic pathways. There can be either the ADE2 process, which stands for addition electrophilic bimolecular, or there can be ADE3 process, which stands for addition electrophilic termolecular. And let us know about them in more detail, because this is something new for you. You have till now only studied about addition and not gone into these details of bimolecular or termolecular. Dissociation of electrophile reagent and subsequent attack of the alkene to electrophile resulting in the formation of carbocation intermediate is the ADE2 process. As you can see here, the alkene getting attacked with E plus, we get this intermediate carbocation and then Y minus. There can be two routes here, that is in ADE2 process, formation of carbocation ion pair from alkene and the reagent. The two ions may combine directly to give product, or they may lead to a free carbocation, as you can see here, that is alkene when it is attacked by E plus, Y minus, you get this carbocation, and immediately it can be attacked with Y minus, that is the directly they will be attacked, or there is a free carbocation which is formed and then attack happens. The formation of a bridged intermediate with the electrophile and subsequent attack by the nucleophile leading to cleavage of the bridge and formation of product is also ED2 process. As you can see here, there is a alkene and E plus when it is attacking, it will form a bridge, that is you can see a 3-member cyclic ring getting formed, and then the Y minus attacks on this. Coming to the ADE3 process, the concerted addition of electrophile and nucleophile to C-C double bond is actually the ADE3 process. So what is happening here? The C-C double bond, you can see the EY is coming close to this C-C double bond, and then there is a simultaneous attack of E and Y, and you are getting the formation of this addition product. So you can see there are 3 molecules which are involved, and that is why it is a termolecular addition electrophilic process. So thus, based on the nature of the electrophile and the relative stability of the intermediates involved, any one of these mechanisms can operate. For example, if proton is one of the strongest electrophile and its addition usually will follow the first mechanism, that is the formation of carbocation. On the other hand, addition of halogens usually involve a bridge intermediate, that is the second mechanism is followed, and all such instances and further mechanistic insights, they are detailed with respect to addition of various reagents to alkenes in the sections which will be dealing. So first of all, let us take the case of electrophilic addition of hydrogen halides to alkenes. The general reaction can be represented as shown here. You are having alkene and hydrogen halide, and out of hydrogen halide the hydrogen is delta plus, X is delta minus, and then there will be addition of H and X and you get this alkyl halide. As discussed before, hydrogen halides, that is HCl, HBr, HF or HI, they will undergo polar addition with alkenes, and the electrophile H plus adds up first to form a carbocation intermediate, and subsequently the nucleophilic part of the reagent then combines with the carbocation to yield the addition product, as you can see in these equations. The reactivity of hydrogen halides parallels their acid strength. Hydrogen iodide reacts with alkenes at the fastest rate, followed by HBr, then followed by HCl, and HF is the slowest. This can be attributed to the fact that as the halogen atoms get bigger, the strength of the hydrogen halogen bond falls. With unsymmetrical alkenes, the reaction is highly regioselective and follows the Markovnikov's rule. That is, the hydrogen will add to the carbon which has larger number of hydrogen atoms in, and the halogen will add to the carbon which will bear the carbocation. But here one thing you have to keep in mind, in between if the rearrangement can happen, it will occur, and the most stable intermediate carbocation so formed after rearrangement will be then attacked by the negative part, and you will get the corresponding addition product. So for example, the addition of HBr 2-methyl but2-ene, you can see here, first the H plus attacks, you get this carbocation, and then followed by Br minus you will be getting. And clearly out of these two routes, the Markovnikov route is giving you the major product. This regioselectivity is a direct result of the relative stability of the possible carbocations involved in the reaction. The tertiary carbocation is more stable than the secondary carbocation, and in turn it is more stable than primary. So, but in this particular example, out of tertiary and secondary, tertiary will be preferred, and the observed product is in accordance to the Markovnikov rule. Sometimes the carbocation intermediates can also undergo rearrangement to generate a more stable carbocation, and if conditions permit, one may observe a different product than expected. For example, the addition of HCl with 3-methyl-1-butene is expected to produce 2-chloro-3-methyl-butane, but a mixture of 2-chloro-3-methyl-butane and 2-chloro-2-methyl-butane is obtained, out of which the latter is major, and this can be clearly attributed to the rearrangement of the initially formed carbocation to the more stable tertiary carbocation via a hydride shift, as you can see here. So, initially you can see it is the secondary carbocation formed, and as this hydride gets shifted, there will be formation of more stable tertiary carbocation, which will be then attacked by Cl- to give the major addition product. In some cases, the mechanism of addition follows a termolecular process, that is ADE3 process, which is mechanism 4 as we have discussed earlier. And if we consider the example here, the addition of HBr to cyclopentene, addition of HCl to 1-methyl-cyclopentene and cyclohexene, and to 2-methyl-1-butene, etc., they will be following this. With HCl, the reaction of disulfur alkenes is quite slow, and use of silica or alumina as heterogeneous catalysis is found to accelerate the rate of reaction. This is possibly due to interaction of silica aluminium with HCl, aiding in the polarization of the reagent for subsequent addition to the alkene. So, you can see here that the HCl, which is being attacked to the alkene, that is getting polarized by this silica, and it will be ultimately helping the addition. The stereochemistry of the addition of hydrogen halides to alkene is usually anti and is in accordance to the belief that attack of halide ions occurs from the opposite side of the pi bond to which the proton is there. So, if you have an alkene, if H plus attacks from here, the halide will be adding from the other side. However, the stereochemistry is temperature and solvent dependent and also varies with different alkene substrates. For example, addition of HCl to 1,2-dimethyl cyclohexene is NT at room temperature, but syn addition product dominates at -78 degrees centigrade. This variation in stereochemistry is actually a direct result of the variation in mechanism of addition at different conditions. Thus, if an ion pair mechanism operates, then usually syn addition predominates. Syn addition is found to prevail when the alkene is in conjugation with a group that can stabilize the carbocation. Thus, styrenes, where the phenyl group is in conjugation with C-C double bond, usually will show syn addition with the formation of an ion pair with more stable benzylic carbocations as the intermediate. Thus, when the stable intermediates having the halide ion on same phase of the molecule collapse together faster than undergoing rotation, it leads to syn product. So, you can see here that on this styrene molecule, the HX is adding and very fast the H plus attacks, and before the rotation can happen, so that the attack from other side is possible, it will be attacking and there is a syn addition which is happening. Let us consider the addition of sulfuric acid to alkenes. Similar to the HX addition, H2SO4 also reacts with alkene to get the alkyl hydrogen sulfates, as you can see in this equation. So, there is the addition of H and OSO3H. The mechanism here also is similar to HX addition of alkenes, and H plus acts as the electrophilic part, wherever the remaining the HSO4 minus will attack as the nucleophilic part of the reagent. The addition here also will obey the Markovnikov's rule. So, you can see this mechanism, that how the H plus attacks, you get the carbocation, and then followed by the remaining HSO4 minus, which will be attacking to the carbocation, and you get the addition product. The resulting alkyl hydrogen sulfate can further be efficiently hydrolyzed by heating it with water to give an alcohol. So, wherever you have this OSO3H, this part gets replaced with OH, that is the hydrolysis of OS bond is taking and you are getting this OH. However, only the mono or disubstituted alkenes of the type RCH double bond CHR, they undergo these reactions with sulfuric acid. With the disubstituted alkenes of the types R2C double bond CH2, that is the terminal alkenes, along with tri-substituted and tetra-substituted alkenes, the formation of alkyl hydrogen sulfate is not observed. Instead, sulfuric acid may catalyze the dimerization or polymerization of the alkenes. For example, the 2-methyl propene will give a mixture of these two dimeric products as shown. And this is attributed to the formation of more stable carbocation, which may itself act as an electrophile and attack another alkene molecule, resulting in dimerization. So, this you can clearly see here, the H plus is attacking on this alkene and then you are getting this carbocation. This carbocation in turn acting as an electrophile and it attacks on the double bond, and see the significance that this being terminal, it is less sterically hindered. So, this big electrophile can attack. Had it been disubstituted from both the sides, this attack would have been not permitted. So, this leads to this carbocation and in turn this carbocation can again attack further, or it can be addition of OSO3H to this particular stage also. Next is the addition of halides to alkenes. Halogens adds to the alkenes via electrophilic addition mechanism to generate the vicinal dihalides, and out of these halogens the order of reactivity is fluorine is most reactive, followed by chlorine, followed by bromine and then followed by iodine. And usually this addition is anti, that is you can notice that as shown here, out of these two X2, one X is being added from one side of the molecule and the other is added from the other side of the molecule. And this is because the mechanism is involving the formation of a bridged intermediate, that is a halonium ion. So, addition of bromine, for example, if we consider to an alkene, it will result in the formation of this cyclic bromonium ion as you can see here. So, this cyclic bromonium ion obviously will have the steric hindrance on the top and the other Br will be attacking from the lower side, so that this Br opens the ring here. So, because of this cyclic bromonium ion, if the one Br which is attacked as Br plus is on this side, the other Br will be attacking from this, and ultimately one Br is here and other is here, that is there is a anti-addition which happens. So, this you can see it is being shown here. For example, cyclopentene will give trans 1,2-dibromocyclopentane when it is reacted with bromine. However, substantial syn addition has also been observed, particularly in alkenes with phenyl substituents, which significantly stabilize the carbocationic center and in effect they diminish the strength of the bridging bromonium ion. Thus, the presence of a carbocation in equilibrium with a weak bridging intermediate will be leading to a loss in stereoselectivity. So, as you can see here that if you have this phenyl as a substituent and in the precursor alkene, so this bridge carbocation which is formed, which is the bromonium ion, will be breaking this and forming this more stable benzylic carbocation, and immediately then further it can be attacked by Br minus, which can happen from the same side as well, and that is why there is a loss in stereoselectivity. So, there is a greater syn addition which can happen rather than only addition which is happening in the anti mode for halogen. Now, coming to the formation of halohydrins. When the halogenation of alkenes takes place in the presence of a nucleophilic solvent, a nucleophile different from the halide can open the halonium ring. When the solvent is water, halohydrins are formed and the reaction will follow the Markovnikov's rule and has stereospecific anti-orientation. For example, you can see here, once you have formed this bromonium cyclic intermediate, and if you have aqueous medium, that is you are treating bromine with water, then first the Br plus will be attacking to give you cyclic bromonium ion, and then to this cyclic bromonium ion, rather than the Br minus attacking to give you a dibromide, water can attack as a nucleophile and it will lead to the formation of this halohydrin or bromohydrin if we are taking bromine. Coming to the addition of water and alcohols. Water and alcohols cannot themselves react with the alkenes as they are not so electrophilic, rather they are nucleophilic. However, their electrophilic addition to alkenes is catalyzed by presence of small amount of acids such as HCl or H2SO4, which can promote the water or alcohol to provide an electrophile to initiate the reaction. The mechanism of acid catalyzed hydration you can see here. Let us take the case of propene as an example. The alkene double bond will be attacked by H plus, and the H plus is coming from the acid we have added here, sulfuric acid, which will result into formation of H3O plus in aqueous medium, and from this H3O plus this alkene is taking the proton, giving you a carbocation, and then the water will be now attacking readily as a nucleophile. So, this carbocation center will be attacked by water and then followed by deprotonation, you get the corresponding alcohol. Similar mechanism also operates in the case of acid catalyzed alcohol addition to alkenes, resulting in an ether product. So, again here if we consider this mechanism, the alkene when attacked with alcohol, so the proton will transfer here and the remaining alcohol will now attack as a nucleophile to this carbocation, and followed by deprotonation you get the corresponding ether. Now let us move to the oxymercuration reduction reaction. The name itself is telling you it is a two-step process. In the first step it is the oxymercuration and the second is the reduction which is taking place. It is actually the first step which is the addition or the electrophilic addition to the alkene. Alkenes can be converted to alcohols via these two processes, and overall it seems that there is a Markovnikov orientation of water attacking to the double bond and giving you the corresponding alcohols. So, you can see here in this equation the alkene is reacted with aqueous mercuric acetate, and as a result there is a formation of addition, you can see OH and HgOAc. Mind it, out of these HgOAc is the electrophile and OH minus is the nucleophile. And further in the second step with reduction with sodium borohydride, there will be replacement of this HgOAc with H, and that is how you are getting the corresponding reduced product which is alcohol. And overall notice that the addition of H and OH is happening in a Markovnikov manner to the alkene. The addition of water to alkenes by this method has some advantages over the acid catalyzed addition that you have studied earlier. First is that it does not require acidic condition which are detrimental to many organic substrate. So, if there is a side functionality which can be affected by that condition, that may be damaged. So, here this has an advantage. The other advantage is that no carbocation intermediate is formed, and so carbocation rearrangement will not happen. In the first step of the mechanism, the electrophilic mercury of mercuric acetate will add to the double bond, and this results in the formation of a bridged mercurium ion analogous to the halonium ion in the addition of halogens that we have discussed. Subsequent attack by the water at the more substituted carbon of the mercurium ion, which leads to a more stable transition state, eventually leads to the generation of an organomercurial alcohol. That is, there is the addition of OH and HgOAc. And to obtain the desired alcohol, demercuration is then achieved by the reaction with sodium borohydride, which will replace mercury species with the hydrogen atom, as you can see here. The reaction also leads to addition product with anti-orientation. When the reaction is performed in alcohol instead of water, it will lead to the formation of organomercurial ether, which on subsequent reduction with NaBH4 will lead to an ether product, as you can see here, that is HgOAc twice in presence of ROH. There will be addition of OR and HgOAc, and with sodium borohydride this HgOAc can be replaced with H. The anti-orientation is happening here also, and notice that anti is happening because of the bridged mercurium intermediate which is formed. Coming to some other electrophilic additions happening to alkene, let us consider the addition of electrophilic sulfur and selenium reagents. Compounds of the general formula RSX or RSCX, where X is more electronegative element than sulfur or selenium respectively, they can undergo addition with alkenes and they will involve a bridged intermediate, as you can see here, and the resulting product will be anti-product and it will be following the Markovnikov rule. So, you can notice in both of these examples the RSCl and RSCCl, that addition is happening to the alkene and the intermediate is this bridged intermediate. Then coming to hydroboration. In hydroboration, it is the borane which is BH3 or alkyl boranes, they add to the carbon-carbon double bond, and this is a concerted process leading to syn addition. So, what happens is both the alkenes and BH3 will be adding simultaneously, that is the BH3 will not break into components, one component adding first and the other adding later, but entire molecules, both of them add simultaneously and both the parts of adding are coming from same side. So, it is the syn addition which will happen. The resulting organoborane is usually oxidized to give an alcohol product with anti-Markovnikov orientation. So, for example, you can see in this reaction, this alkene when it is adding H and BH2 parts of BH3, this is how the in between 4-membered transition state will be there, and there will be addition of H and BH2, and ultimately when this is further treated with H2O2 in alkaline medium, the BH2 gets replaced with OH. In between there is a trialkyl borane stage. So, this reaction you will be subsequently studying in more detail in a later module. Another reaction is epoxidation. Epoxidation is also essentially a concerted electrophilic addition. It is also analogous to halogenation and addition of sulfur or selenium compounds that we have discussed just now, and this will also involve a 3-member ring, but the epoxide ring is quite stable and it can be isolated. So, you can see here that this C-C double bond, it is when this is added with these peroxy acid, this is how the transfer of oxygen is happening to the alkene, leading to the formation of this epoxide via this cyclic electronic transfer. The next reaction to discuss is syn-1,2 hydroxylation of alkenes with osmium tetroxide or alkaline KMnO4. Alkenes can undergo oxidation to syn-1,2 diols with either alkaline osmium tetroxide or alkaline potassium permanganate. So, you can see here the general reaction, this alkene when subjected to this, the OH and OH will be adding from same side, that is the syn addition will be happening. The reaction with osmium tetroxide involves a concerted electrophilic addition generating an osmate ester which is hydrolyzed to a syn diol by hydrogen peroxide, and this also reoxidizes the osmium catalyst. So, this you can see here, this cyclopentene, how it is forming this concerted electrophilic addition reaction, and subsequently this cyclic species when it is hydrolyzed with H2O2, there will be formation of OH and OH on the syn side, that is there is a syn addition which is happening, and very analogous reactions occurs with alkaline KMnO4. Some preliminary reaction you have already studied. So, this module has given you an overview of the C-C double bond reactions, and we have focused about the electrophilic addition reactions, what are the different mechanisms and the examples which are covered in these different mechanisms. So, dear students, let us summarize what we have learned in this module. We have studied that compounds with unsaturated bonds have a relatively loosely bound region of high electron density, and they readily react with substances which will be adding to them, that is the addition to the double bond. Most common among the addition reactions of carbon-carbon multiple bonds is the electrophilic addition reaction, because they are multiple bonds are electron rich. So, the electrophiles will be adding, and that is the electrophilic addition reactions are the most common. Polar additions are involved in which a reagent gets polarized into electrophile and nucleophile parts and then undergoes the addition with the alkene. We have also studied that electrophilic polar additions may involve any of the four main pathways that include either an ADE2 process, that is the formation of a stable carbocation, or carbocation ion pair, or bridged intermediate, or it can be an ADE3 process, which is the concerted addition of electrophile and nucleophile to the C-C double bond in a termolecular process. We also studied that usually the Markovnikov rule is followed in the addition, and the stereochemistry is dependent upon the mechanistic pathway which is involved. Bridged intermediates, as observed in halogenation of alkenes, give stereospecific anti-orientation, while the ion pair will lead to the specifically syn additions. Alkenes undergo many electrophilic additions of synthetic importance that include addition of HX, addition of halides, acid-catalyzed hydration, Oxymercuration reduction, sulfinylation, selenylation, hydroboration, etc. Some electrophilic addition they show concerted mechanism such as hydroboration, epoxidation with peroxy acids, and the syn-1,2 dihydroxylation of alkenes. We also studied that the stable carbocation may sometimes lead to dimerization and polymerization of the alkenes.